So let me pose a concrete question. So you have a graph with n vertices. So each edge E is on with probability P and is off with probability 1 minus P. Different edges are independent. So you can calculate the expected number of edges, for example. It's n choose 2 times p. The expected number of triangles is n choose 3 times p cubed. Okay. Now there is a little ambiguity in how you count. You know, if you have a triangle, say PQR, or vertices numbered 1, 2, 3, is this one triangle or 3 triangles? You can relabel them and you get another triangle. So the easiest way to avoid the problem is to look at the ratio the number of whatever you want in your graph divided by the number in a complete graph. So long as you count them in the same way, both in numerator and denominator, that 6 factorial will cancel out. So this ratio is just p for the edges and p cubed for the triangles. There is in fact a law of large numbers. For edges, just the usual law of large numbers because they are independent. But for triangles, there is overlap. But you can count how many triangles overlap and you can compute the variance and it's negligible. So you can still calculate and show that the law of large numbers is valid. But large deviations is different. It's not clear how to do large deviations with the number of triangles. More precisely, I want to be able to answer the following question. If I have the number, the ratio of triangles is greater than p cubed, so I have more triangles. Then what can you say about the graph? How did I get more triangles? There are 2 different ways of getting more triangles. You can simply could have had more edges, or the edges could have formed a clique. If the edges formed a clique and concentrate in one area, then you get more triangles. So the question is, can you say what happened here. That requires understanding some of the large deviations here and what caused this large deviation. Similarly, if we have fewer triangles, it could be because you had fewer edges, or maybe the graph somehow became a bipartite graph with links only between the two sides, and then there are no triangles. So that's another possibility. So you don't know which possibility actually occurred. So can you resolve all these things by proving a large deviation result? And so that you can condition with respect to the number of triangles and then say something about the graph as a whole. So in order to do such things, triangles are just a special case. It could be any finite graph you could condition with respect to quadrilaterals, stars, whatever you like. So what we are trying to analyze is, you look at, let G be a finite graph, and then you compute the number of occurrences of the finite graph in your graph and divide it by the number in a complete graph. Call that ratio can't call both of them G, maybe I should call this H. It's gamma G of H. So it's the ratio, some measure of how often H occurs in G. So I have a sequence of graphs Gn n goes to infinity. Before you prove any large deviation result for a sequence of objects, first of all, the large deviation has to take place in some space. You need a space. So all these graphs have to be embedded in a space. So there should be some kind of an object in which all graphs of all sizes live comfortably together. Well, there is one possibility, which is you could represent a graph by a matrix, zeros and ones. So you can make Aij equal to 1 if I is connected to j by an edge, Aij equal to 0 otherwise. And I'll make all the diagonals 0 because you don't want any edges connecting to yourself. That's still not satisfactory because the size of the matrix now depends on n. You want them all in one object. So we can do that by saying, okay, I don't really have a matrix. I have a unit interval 0 to 1. 0 to 1, so I have the unit square, which is divided into n intervals. And these Aij's, zeros and ones, are just entries here, depending on which edges are connected. So I just embed my matrix in the square. Now all my graphs are functions on the square. So my graph just got replaced by a function fxy, which is 0 and 1. In fact, it's 0 or 1 on the unit square. So I have the space of functions. Now I can try to do large deviations there. Now, how can I recover the objects I'm interested in here? One can check that the proportion of edges is just the double integral fxy dx dy. And the proportion of triangles is triple integral fxy fyz fzx dx dy dz. Calculated, the trace of the cube gives you the number of triangles. In fact, you can find the proportion of any graph, H here. H has vertices, so you have as many variables as there are vertices. And there are edges, you have as many edges in here over all I to j that are edges, and that gives you the count for the number of embeddings of any finite graph. So all this information about the number of times a particular subgraph, finite graph occurs in my big graph can all be captured by this function. So if we can prove a large deviation theorem for this function, then I can go home. Well, this function basically comes from independent random variables. So the entropy here is just f log f over p plus 1 minus f log 1 minus f over 1 minus p. That's the basic effect. And your actual rate function is going to be dx dy double integral. That will be a 1/2 because you only have to do it for the triangle. The other side is automatic. Okay. And that's because basically what you are saying is that if you have some function fxy and you chop it up into little things, you know roughly how many edges you want here in order to get the correct integral, assuming everything is continuous. So locally you find out the entropy and then integrate it because they're all independent, add it up. So in some sense it's totally elementary to prove that there is a large deviation with this rate function for the measures induced by these zeros and ones as n goes to infinity. The problem is it's totally useless. It's totally useless because in what topology am I proving this large deviation? I have zeros and ones, and the limit wants to be anything but 0 or 1. It's a continuous function. It's a function that takes all values between 0 and 1. So the convergence has to be in weak topology. And my functions that I am interested in are highly nonlinear. So weak topology cannot control anything. it's clear the weak topology doesn't control, because I think I gave this example last time. If you take the vertices, if you take your graph G, if you relabel the vertices, then this picture changes, because it's a permutation of the rows and columns. And that means your weak limit may also change. But so, and with weak limit changes, these integrals may be different. So it's not clear what you're doing. In fact, the extreme example of it is that if you have a graph or you have two sets and you have edge between everything from one to the other, and that's all you have. And if you think of them as odd and even, then the limit is evenly split, because they're odd and even or nicely interspaced. But if you happen to order the odd ones first and the even ones next, then the limit would look like this. This predicts lots of triangles. This predicts no triangles. So the weak topology is totally useless for this limit, so you cannot control it. And the strong topology is not going to work either. So you need to discover an in-between topology. Okay. You can start with the minimalist point of view. If I have a certain function, certain class of functions to be continuous in a certain topology, it's natural to define the topology as the smallest topology in which these functions are continuous. So let's do that. So you have these ratios. I say that Gn, the graph tends to G, if sigma Gn of H tends to limit sigma H. So I say that a sequence of graph converges if this limit converges for every H. Okay. Well, that's a perfectly reasonable thing to do. The set of such H's are only countable, so I can even cook up a metric that does this convergence the usual way. I take the difference, divide by 1 over 2 to the n or something like that. So exercise in real variables and you sum. Okay. And these are all between 0 and 1. So the space you are going to end up with is going to be a compact space. But you have no idea what the end is. To the end, you get a function sigma g, sigma h, which come as the limit of these things. So the first question is, what sigmas are limits? can you characterize the sigmas that are limits of these things? We have a clue. You can think of this. It would be nice if you had a theorem that any limit can be represented in this manner for some f. For triangles, for general gamma, it's this one. So gamma, any sigma h is this for some choice of f. It would be a nice theorem to have. Okay. And what would be the topology? Well, you can transfer the topology here. So the topology that I want on these functions is that all these functions are continuous. These integrals, so let me define them here. Think of it like that. Gamma are the edges. These are the vertices. So think of this as a function of f. I say that a sequence fn tends to f if sigma hf says to sigma hfn tends to sigma hf for every h. H is a finite graph that has edges gamma and vertices xi. Okay, this is reasonable. And it's clear that it's some kind of topology, but it's not clear what it is. Okay. Then here, looks like whatever you get must be compact. It's not clear that what you have here is compact either. And you can ask another question. You said that the limit is representable in this manner. Is the representation unique? In other words, can the same sigma can be represented some other g? If you think about it, there is a symmetry in the problem. Permutation symmetry of the vertices hasn't gone away. So that somehow should be reflected here, and it's reflected as measure-preserving transformations of the unit interval. If you map the unit interval measurably onto itself so that it preserves Lebesgue measure, then these integrals don't change. So long as you use the same measure-preserving transformation on both sides of the square. Okay? Because, just replacing f by f sigma xi sigma xj can be absorbed in the by change of variables. So your actual space that you want to work with if you cannot by omega, your space of functions between 0 and 1 on the square, and you have the group of measure-preserving transformations at the unit interval, that's the space on which you want to do large deviations, if you can find what the topology is. And you have to prove somehow that space is compact in order to do that. What gives you compactness? Notice this group is not a compact group, it's a humongous group. Big group. Turns out that this topology we are interested in is not that difficult to describe. Weak topology means you say that integral fxy fn xy against any test function tends to that's the weak topology for functions phi bounded by 1. Bounded continuous or bounded doesn't matter because my fn's are bounded by 1. So strong topology is exactly the same thing, but there is a sup over phi less than or equal to 1 that makes a strong topology once it's uniform. Weak topology is valid for each phi, and strong topology is valid uniformly. Or in terms of sets, strong topology means corresponding measures converging in variation to 0, strong topology. Weak topology, since they're all bounded densities anyway, is just the same thing, just for each A, without any uniformity. But A is any Borel set in square. The in-between topology, which is referred to cut topology, or the cut metric, the functions you take are of the form product function of x times the function of y. They are both arbitrary and they are both bounded by 1, and you take the sup over all of them. you don't take the sup over all functions of two variables. You take the sup over functions that factor into a function of one variable x times the function of the variable. Or in terms of Borel sets, you take the sup over sets A of the form all E cross F rectangles. But E and F are arbitrary Borel sets in one dimension, not just intervals. The E and F are arbitrary Borel sets in one dimension, and you take the product. And that's the cut topology. Notice this topology is weaker than the strong topology, is stronger than the weak topology, but still the space is not compact. The space is not compact because when you project it onto one of the axes, that means you are taking F to be whole space, you are still taking sup over all E. So the projections on the one of the variables, they converge strongly. So the space cannot be compact. But once you mod out by measure-presuming transformations on the line, that disappears. So there is a chance that the equivalence classes modulo measure-presuming transformations can be compact. So I want to tell you a little story at this point. So it was maybe 7 years ago, around that time when Saurav Chatterjee was my colleague at Courant, we were discussing this problem, and we had sort of worked all this out and realized what we really needed was some way of expressing this matrix by permuting the coordinates, getting it to a more decent form. So a colleague, Joel Spencer, who combinatorialist number theory, I was having lunch, and I told him, look, I need something like that. I have no idea how to prove it. And he told me, you don't have to prove it, it exists. It's called Shimradi's lemma. So I said, okay. So I went through Shimradi's lemma. But now the hard proof at that time, but now there is a easier proof of Shimradi's regularity lemma, which makes this a little more clear. And that's what I'll present now.
Laser pointer and also
I don't know why it's called a lemma. It's really a powerful theorem. So you have a graph G. Let epsilon greater than 0 be given. Then there is an L that depends only on epsilon, nothing else. Such that any graph with more than n vertices enjoys the following. epsilon is given, n depends on epsilon. So given any n, given any epsilon, I can choose an n with certain properties. The properties will involve epsilon. Ravi, okay? You have a question? Okay. So given any m, there is an m that depends on m and epsilon such that there is a partition of the vertices into sets A0, A1, A2, AL with certain properties. First property is that the size of A0 is less than epsilon. The size of A1, the rest of them are all equal to some numbers. I asked D, they are epsilon n. D the pairs AIAJ all but epsilon L square satisfy the following. If BI is a subset of AI and BJ is a subset of AJ and the number of size of BI is bigger than epsilon AI and the size of BJ is bigger than epsilon AJ, then the number of edges connecting BI and BJ divided by BI BJ minus the number of edges connecting AI AJ divided by mod AI mod AJ, the difference between them is less than epsilon. That's the lemma. What does it say? What it says is, let me give an interpretation for this. Given any m, there is an m. Well, the role is the L I choose here is between, I didn't say that this L is between m and m. Let me explain what the idea behind it, and then you can parse this. I hope I wrote everything down without leaving anything. No, the size of all these partitioning sets are equal. See, the set of vertices is divided into a finite collection. There is one exceptional collection which is called A0. Those are the bad guys that are thrown away somehow, epsilon fraction. And all the rest of them are equal size. And how many of them, I don't know in the beginning. But you give me any number, I can give you a finite range for it. If you tell me m is 1,000, my capital L, depending on epsilon, may be 1,000,000. So L could be anywhere in that range. I can't tell beforehand. Not only that, that L can vary with the graph. Doesn't have to be the same for each graph. Notice the point of the theorem is that n, the size of the graph, depends only on epsilon. So long as the graph size exceeds epsilon, all this is valid. John? No, size of the graph, no, as soon as n epsilon is n depending on epsilon. You know. Okay. See, look at the following situation. Yeah. I'll explain it. It all falls into place. Imagine the following situation. You have a graph. There's some junk here you don't care about. Maybe 0 here, nothing connects to anything there. And the rest of it use some numbers Pij, probabilities, maybe for having an edge connecting those two. Now, this is not really a random graph. This is only probabilities. But you can draw a sample from it and you'll have a random graph. So for every edge, possible edge here, you sample independently with this probability, and you construct a random graph. Okay. That random graph will satisfy more or less all these properties. Because if you have a graph and independently drawn, and the proportion is something, if you take a subset which is substantive, the proportion will be the same as the whole proportion. That's what this says. What this says really is any graph of big size is uniformly close. All big graphs are uniformly close to random graphs. And the random graph you generate is just from a finite number of grids. And the number of grids you have to choose is independent of n. It depends only on epsilon. Close in what topology? Close in what topology? Yeah, you have to. That's really what this says in some sense. What it says is that, one way of saying it, you get any graph and you produce this matrix of zeros and ones. Okay. By permuting the rows and columns with the same permutation, they're just relabeling the vertices, I can make it very close to a finite grid. And that gives you compactness. Is that clear? So we need to prove this somehow. Okay. So let me define some numbers. Given two disjoint set of vertices, EAB is the number of edges that connect the two. RAB the way to interpret RAB is, imagine the vertices having a probability distribution of 1 over n equally weighted. So what this is, if we choose randomly something from A and something from B, what is the probability there is an edge connecting them? That's the conditional probability of that. So if you have a partition like this, I want to define a functional of the partition. Now, notice the difference between these two. If you think about it for a second, A naught is simply viewed as a collection of single point partitions. So if you have only one member in the partition, it will be what it is linked to divided by n square. And that's what this is. So A0 consists of just one element A. And for each such A, there is one partition. So that's why A0 is special, because these are single point partitions, possibly with edges connected to all others. Okay, this is function. Now, here is the A naught itself, single point partitions, and AI looks like this. And what this whole thing is, if you look at the function f(x,y) and think of the partition as a sigma field, if you like, expected value of that given P cross P, the square of this and the expectation of this is what this is. Basically, these things compute the conditional expectation, you square it, you weight it by the probability and add it. It's all discrete, so you just compute the conditional probabilities and add them up. So that's what you're computing here. So one thing to notice, if you refine a partition in some way, make the sigma field bigger, this goes up. This goes up by the difference between the two. L2 norm of the difference between the two, because there's the difference between one projection and another projection. And so if you look at the two projected values, and the norm square of the difference is the amount by which the norm goes up. So you know what happens when you refine these things, the norm goes up. But how big can this be? It's easy to see that this is bounded by at most 1. Because this is less than or equal to 1, it's aj by n square, it's some 2 half or 1, some 1 is good enough. So what I'm going to do is I'm going to start with a partition, and if partition doesn't satisfy this condition, I will refine it. When I refine it, I will show that this thing goes up. I will show that it will go up by a definite amount. Each time I refine, it goes up by a certain amount. I can't do it more than a finite time because I can't exceed 1. So at some time, I cannot refine it anymore. When I can't refine it anymore, lemma is satisfied. That's the end of proof. No, if you want it to go up, you have to do it right. Any refinement will go up, but you want to go up by a certain amount, fixed amount. So at some point I'm here. In this process, forget how to start. Assume you started somewhere, you're going along and you're at some place. At some place, you have these sets. Some k of them maybe. The current value of L may be k. And they're all of size d. And let me assume that I always have this. I'm going to always make sure that this condition is always satisfied, so I don't have to worry about it each time. I'll check in the end that during my finite process, it never goes up beyond epsilon n, so that's okay. And epsilon itself, I can assume, is sufficiently small, say less than a quarter. So this A naught is, so now what do I need? Why is it not satisfied? Because there are epsilon L square bad pairs. I only have to deal with bad pairs. So there are epsilon L square bad guys. Epsilon k square. Which do not satisfy the condition. What do you mean the condition is not satisfied? That means they have a bi, bj, mod bi bigger or equal to epsilon mod ai, mod bj greater than or equal to epsilon mod bj, and and E R AIAJ minus R BIBJ is greater than epsilon. Okay. So here is AI. Here is a BI with sizable mass, which is behaving badly. So that gives me a natural decomposition splitting here. That's the split I want to do. So divide AI into two pieces. Similarly, AJ gets divided into two pieces according to AJ and BJ. So let's do it a little more carefully. So I find a bad thing here, bad thing here, bad thing here. Bad thing here splits up this and this. This bad thing splits up here and here. This bad thing splits here and here. But I may have a bad thing here, which will split up again this into this. So the same interval can be split up many times. Okay? But in the end, it's a refinement. I do all the refinements possible. But each time I refine because of this, you can do the calculation and you can see that it goes up by a certain amount, which depends only on epsilon, nothing else. And the amount by which it goes up is epsilon to the 4d square by n square. Okay? It's just comes by because you look at it, you are going to square the difference between the two. Difference between the two is epsilon. You square it, you get epsilon square, and then the probability is d over n. Which one? What? L is anyway, I'm not saying L can depend on epsilon. See, L is between here and here. And then there are epsilon k square such pairs, because it's not just one pair. One pair is okay, I'll accept. So let's add that too. So it gives you epsilon to the 5 e square k square divided by n square. Okay? But dk plus epsilon n is n. That tells me that dk is bigger than or equal to 1 minus epsilon n, which is 3/4 n. So dk square over n square is bigger than or equal to 1/2. 1/2. So this is greater than or equal to epsilon to the 5 over 2. So if I had to go on, I gain at least a fixed amount. It depends only on epsilon. So I cannot go on more than twice epsilon to the minus 5 steps. I should stop. So all I need to worry about is I don't build up A naught. Okay. Now I need to, I was little, now it's not enough if it just goes up, because then I subdivided it, and then I end up with partitions of assorted sizes. So I can't go to the next step, so I had to clean up the mess a little bit. The way I clean up the mess is, okay, I'm willing to now subdivide these things into smaller sizes, and whatever is left I'll throw in A naught. That's how A naught builds up. So the new d prime is, I think it's 4, some huge number. D over 4 to the k. So I shrink the sizes at the next step by a huge factor. Then I will have maximum number I'll be left over with is how many cells do I have? How many pieces do I have cut up? Okay. That depends on how many times does each one get cut. The maximum possible for each one to be cut is when it's paired with everybody else. So k minus 1 cuttings is what is possible for each one, and that will generate at most 2 to the k minus 1. Right? So k like that for each cell. So the new one we started out with, at most this many. Okay. So that's how many boxes you end up with after you chop it up. And then each box you divide into du over 4 to the k size sub-boxes uniformly. And what's left, each piece that's left is at most one box. So this times this is what you add to C naught. And initially you choose a k naught. You're not going to be any bigger than that. And the number of steps you're going to make is at most this much. So this is at most what you can add to your original thing. And you count everything and you make sure that's less than epsilon. You have control in all of these things, and that lets you how to choose k naught. And once you choose k naught, that tells you how to choose n. You have not chosen n yet. So this allows you to choose k naught because you want the initial thing, the sum of all of these things, to be less than epsilon n. That puts a demand on k naught, and then that will put a demand on n. So what does it say in the end? What? Well, I think k naught has to be such that to work it out, you want 1 over 2 to the k naught to be less than epsilon to the 6 by 2. That's the choice of k naught. And then n to be larger than k naught over epsilon. Something like that. Those are the choices you have to make in the end to make the whole thing work. Just comes from adding these up. Because everything works without any having to choose anything. You just want to, because you're throwing all the problems on A naught, and you just want to keep count that A naught doesn't get too big. Okay, that is Chamarini's lemma. And now, what does this lemma tell you? Many things. It tells you, first of all, the quotient is compact because the permutation group essentially brings you within epsilon of this finite complex. This is a compact set even in L1. And you have to check that all this brings you within epsilon of a set of certain set in the cut topology, cut metric. You have to check that. That's I'm not going to check it, but it's just splitting the set up and computing it. Okay, because cut metric means you have to compare on such a set, and you write it as union of AI intersection BJs, A intersection AJs, and then in each piece there is a good piece, and you separate out the good piece. The good piece, the difference is small. The bad pieces, the measure is small, you can throw away, except there is a certain number of bad pieces that you can't control, but their total mass is very small. That's what all of this Chemeredis lemma says. Okay. Now to large deviations. Bound. The difficulty in the upper bound is, although you have compactness in the space of orbits. So you have this orbit, and you have the neighborhood of the orbit. And you want, this is the orbit of maybe some f g. And you want the probability that you are in the some neighborhood of this orbit, you want to estimate is whatever the exponential rate is. Once you have it for neighborhoods, since the space of orbits is compact, then you don't need to worry about anything else. But the orbit is infinitely long, and how do you estimate it? Turns out what you prove is you pick some spot here, orbit of the Bessel-Proswing transformations of the unit interval. That's the orbit. What you need to show is basically that this orbit, because of using the Chemeredis lemma, you need to only worry about the permutation group of it and not the entire Bessel-Proswing group. So use Chemeredis lemma to reduce it to permutation group. So you need to add the probabilities of all these things to the n factorial. Okay? But remember, the large deviation rate function here is e to the minus n square, because there are n square edges. That's where so n factorial is nothing. You can throw it away. It's just n log n. Right? So the infinite length of the orbit doesn't really worry. So the upper bound is okay. The lower bound is a little bit of a problem again, because usually when you prove the law of large numbers, you can't prove the law of large numbers in the strong topology. Prove the law of large numbers in the weak topology. So what you need to prove is the probability that the supremum over E cross F is well behaved in law of large numbers. Again, you can show that if you look at this picture, where you have randomly generated zeros and ones, independent, you can even allow the probability Pij to vary gently like a function of fx over n, y over n, to approach an f. And the sup over E and F is over all Borel sets. You can convince yourself you don't need all Borel sets. It's enough to check all Borel sets that are unions of whole intervals. You don't have to split an interval because everything is constant on intervals. That sigma field is enough. Okay, how many such subsets are there? Well, there are 2 to the n here. There are 2 to the n here. So together there are 2 to the 2n. Your large deviation rate function is e to the minus n square. Doesn't matter. So you do have law of large numbers in the stronger, in the in-between topology. And that's enough to give you a lower bound. And the lower bound, if you prove it for one piece, that's a lower bound for the whole orbit. You don't have to worry about it. So you have both upper and lower bounds. Large deviation for this. But the rate function is just the Bernoulli rate function. Okay. So now you can ask questions about all the issues that we raised about triangles and edges and so on are now calculus of variation problems. That's easier said than done, because calculus of variation problems with huge symmetry are difficult to handle. Turns out, it's a lot of work done by others afterwards, that one thing one can do is, if you are very close to p squared, p cubed for the triangles, and very close to the expected value for other things, then constant is a stable solution. As you're in a region where rate function is convex, and you can't beat constant. So basically it says small perturbations arise from just perturbing the number of edges. Once you move away from that, strange things happen. And there are examples of strange things. And it turns out that many of the extrema are attained at functions which are piecewise constant. So basically, you just divide the square into blocks, and you have different values at different blocks. It's not varying continuously. That's how that stands. Okay. Thank you. You wanted some references, so I'll put up some references. So the paper by Strassen called invariance principle for the law of the iterated logarithm. It appeared in ZW 1964. Volume 3. And then shown the other law of the iterated logarithm, which is a different title on the maximum partial sums of independent identically distributed random variables. Transactions is for American Math Society, volume 64. On the law of iterative logarithm for local times. Communications in Pure and Applied Mathematics, volume 30. Okay. Then Danskar and Varadan, number of distinct sites visited. CPAM volume 32. That's 1979. Then the next one is Schnittmann. Called Brownian motion, obstacles, and random media. Yeah. What?
1979 or 29?
Well, it's 29. I'm not that old yet. The 1998 book. European Journal of Combinatorics. (2011). And expository article in Bulletin of the American Math Society, 2016, and Lubetsky. Replica symmetry. LDP and random graphs. And Radin. Sadum. Singularities. the entropy of large simple graphs. Okay. And some of this work is later work, extends and deals with some of the issues raised. Thank you. Any questions? No. See, what I do is I chop. Each AI can be chopped up several times because it's chopped once with AJ, maybe once with AK, once with something else. So chop them up as you like, as many times as you want. Then you have a whole collection of sets of different sizes. Then I take each one of them, divide them all into size 1/4 to the k times what I started out with, and whatever I do, and what is left, bits and pieces, throw into A0.